We're going to follow that up with looking at our overview of our rules for aromaticity. So there's really three categories that our compounds can fall into: aromatic, anti-aromatic, and non-aromatic. I would kind of make the argument that the aromatic and the non-aromatic are going to be your most commonly labeled. The anti-aromatic, depending on the size of the structure, will sometimes tweak itself so that it becomes non-aromatic instead. Aromatic, incredibly stable, okay? Lots of internal resonance. The anti-aromatic look like there's some stability, but based off of the molecular orbital diagrams that we saw in the aromatic rule video, they end up not being very stable. So they end up being super, super reactive. And then the non-aromatic just are everything else that invalidated the rule sets. So what are the rule sets that we need to be looking at? So aromatic, you need a fully conjugated ring. Okay, so your ring has to go all the way around. That's a ring, sorry. And you need overlapping p orbitals on each of those carbons. That really just means, can you draw resonance? There are some cases that could potentially pop up where it looks like resonance, but the structure wouldn't allow it. Those tend to be rare and few and far between. So if you're seeing an aromatic ring with p orbitals, or the potential for p orbitals, which we'll see in a second, rule 1 would be satisfied. And I just noticed the numbering here is awful. And then rule 2 is that it has to meet Huckel's rule, okay, which is really, the rule explicitly says it's an odd number of electron pairs, or it fits this weird formula. 4n plus 2 is your total pi electrons, where n is 0, 1, 2, 3, 4. And I get people say, well, what is n? N is a number, 0, 1, 2, 3, 4. Right? It doesn't mean anything. It's not the number of electrons. 4n plus 2 is the number of electrons. N is not the number of pairs. Right? N is just a random, not random, but a whole number integer. Okay? And so really what this rule boils down to, which is potentially more relevant for you, is that when we're looking at Huckel's rule, what we want is our electrons, or the number of electrons in our p orbitals, okay, our pi electrons, so let's fix that. We want our pi electrons to be 2, 6, 10, 14, 18. Anybody noticing a pattern here? Or are they just adding 4 each time? So if you memorize aromatic is these guys, you're probably okay. Why not memorize 18 and on? The odds that we're able to draw a structure that get 18 and on easily into an exam, slim to none. Okay, so it's not really worth memorizing those. But if you memorize 2, 6, 10, 14, those are pretty common, with 2, 6, and 10 being very common, okay? 14 being on kind of the verge. How did that apply? Well, to get 2 electrons, 4n plus 2, what was n? N was equal to 0. So 4 times 0 plus 2 is 2. Okay. What if n was 1? 4 times 1 plus 2 is 6, 2, 3, 4. Okay, so that's where the n is coming from. It's just how you would solve this formula. Okay. The anti-aromatic, you still have to have this fully conjugated ring with our overlapping p orbitals. Okay? But where it falls out is that you get an even number of electron pairs, or 4n total pi electrons. Again, I would argue that you could switch this and say, well, I'm just going to memorize the pi electrons being 4, 8, 12, plus 4, 16. Okay? And you now have the pi electrons that you could memorize. Okay? If we look at the examples, we've got our benzene. As soon as you see benzene, it's aromatic. So that's I guess worth memorizing. Okay? If we look at the pairs of pi electrons, so 2, 4, 6 pi electrons, there it is, so it fits. We could also look at it as an odd set of pairs because there's 3 pairs within that. If we move to this goofy looking structure down here, okay, and you might go through and say, well, that doesn't satisfy the first rule, p orbitals. These electrons do have the potential to do resonance. Okay, that is allowed. But the number of electrons within this, we get 2 from the pi bond, and then we get 2 from that lone pair. This is 4 electrons. Those 4 electrons mean that we would be anti-aromatic. Okay? And then the non-aromatic hexane. Okay? It's not cyclic. Okay? Or we could draw cyclohexane. It's cyclic, but no p orbitals. Okay? So no pi bonds. So those are the kind of pieces of things that you should be looking at and considering. Okay, and I need to escape that. So let's try that and see if everything jumps with me. Okay. So you should be able to look at a structure and decide, is it aromatic? Okay. All of the examples that you've seen so far have really been through a carbon pi system, but it doesn't have to be carbons. You can have heteroatoms in there as well. Okay? As long as it satisfies the rules. Our rules say nothing about carbon. It just says conjugated ring with p orbitals. Okay? And that we have to have that proper number of electrons. Okay? So far left, you should have already solved those because those were in the aromaticity video that theoretically you watched. So let's go through and do those. We've got 6 pi electrons. We have rule 1 satisfied. We have rule 2 satisfied with 6 pi. So that one would be aromatic. We move to the next one. Rule 1 is satisfied because we're a cyclic structure with p orbitals. Rule 2, we have only 4 pi electrons. That does not meet Huckel's rule. Okay? That makes it anti-aromatic. And then that last one, rule 1, it's cyclic, right? P orbitals. The hybridization of that carbon is sp3. There is no p orbital. Rule 1 is invalidated, which makes this one non-aromatic. Okay, so with that, we've got 4 more for you to go through and attempt. I'm going to suggest you hit pause, and then we'll encounter a question, and now we can address all of these answers. So if we start with the next one, rule 1, it is cyclic, and we go, oh, but it's not aromatic because, or not p orbitals because we don't have a p orbital there. Well, the hybridization of that carbon, to be a carbocation, there has to be an empty p orbital. So yes, there is a p orbital there. Rule 1 is indeed satisfied. Okay, does it meet Huckel's rule? Okay, well, there's 4 electrons. 4 pi electrons does not meet Huckel's rule. This structure ends up being anti-aromatic. Okay, and we now also have a little discussion that we could address how this anti-aromatic kind of becomes non-aromatic. Okay, anti-aromatic is higher in energy. So structures don't want to be in that high energy state, and so what they will do is attempt to break one of these rules to prevent it from being in that high energy state. We've got a cyclopentane, that 5th carbon, imagine I'm holding my hands in a circle, because I don't want to redraw everything, holding our hands in a circle to represent our cyclopentane. We might say, well, isn't that flat? Well, one of those carbons, particularly that carbocation carbon, can pucker up out, and we get kind of that envelope configuration. That envelope does tweak some of the bond angles because of the double bonds in here, but that now breaks it from having overlapping p orbitals because literally we've moved that p orbital out of alignment with the rest of the other ones. Okay, so that structure kind of runs on this verge between anti-aromatic and non-aromatic. I don't like that, okay, but you can see people asking questions at that level. Okay, you should call it anti-aromatic. If you think the multiple choice or show your work is trying to push you towards non-aromatic, then say non-aromatic and provide that explanation. Okay, next one, not cyclic. Right? Because it's not cyclic, we're looking at non-aromatic. And now we encounter the next one, right? We might go through and say, well, 1, that is cyclic, so it satisfies that rule. And then 2, well, I see 2, 4. Well, that's only 4 pi electrons. Doesn't that make it anti-aromatic? Don't forget the lone pair on that oxygen. One of those lone pairs could donate in, meaning we're 4 pi plus 2, we're at 6 pi electrons. This becomes aromatic. For the pioneering few of you going, but there's another lone pair. Couldn't that lone pair also donate in? Okay, that is a challenging question to answer in this space because we don't have orbitals in front of us to show this. That oxygen is sp3 hybridized. It can squish a little bit the bond angle so that one lone pair shifts into alignment with the rest of the pi system. Okay? I may regret this, but I'm going to attempt to draw this. So there's our pi system, our p orbitals, okay? Lone pair, lone pair, okay? So what the oxygen can do is say, well, but if I donate that pair of electrons by rotating the angle upwards, so that's what we did, we kind of rotated that structure up, now I become aromatic. Well, why would it do that? Remember, aromatic are incredibly stable, so that's a good thing. But as it rotates up, where does that rotate this other lone pair? That puts that lone pair in the plane of the paper, also known as orthogonal or perpendicular to the pi system. Because there is now 0 overlap with the pi system, that lone pair cannot donate in. So if we're looking at a structure that happens to have multiple lone pairs, you could share one lone pair from an atom, okay, from an sp3 atom, and we'll see why that is here in a second. Okay, so an sp3 atom within the ring can share a lone pair. So we could do kind of a, I don't know if it's a corollary, that's horribly spelled. An sp3 with lone pair counts. Okay, with, I guess we should add 1 lone pair can count to your pi system. Which would then take us to the next one. Okay, we've got cyclic, number 1. Okay, so cyclic satisfied. This lone pair could count in, so we do have that pi system. Okay, we counted out, well, that's 6 pi electrons. Again, that pioneering person within our class might say, well, what about the other nitrogen? Doesn't it have a lone pair that it could also donate in? Well, again, we would go back to our drawing, and if that nitrogen was sp2 hybridized, that lone pair is sitting in an orthogonal orbital. It's also in a perpendicular system to the pi bond. Okay? Because it is perpendicular, there is 0 overlap with the pi system, which means you cannot count that lone pair into it. Therefore, straight up aromatic. I should have done that in red. Okay. If you still have questions with that, I don't blame you. Chat it up, office hours. I will try and build a model. I just don't see a model kit obviously around in my office to be able to show that. And even then, I don't know that I'd be able to do it through a recording easily. Okay. So hopefully you've got the ability now to identify aromatic and anti-aromatic, which is really the biggest thing I need you to be able to do. The frost circles, arguably, not really all. Okay, so don't stress a whole lot about those. So why? Why do I care about aromaticity? Well, if we looked at these 2 molecules, how might they react? And so based off of our last unit, we actually addressed what the nitrogen is very capable of doing. Well, that nitrogen has a lone pair of electrons, and as a lone pair, it could donate those electrons. That nitrogen could act as a base or potentially as a nucleophile if you wanted to dig into it. Okay, but that all hinges on that lone pair being available to react. Okay, so are both of these lone pairs available to go outside the structure? Okay, well, if we go through and actually look at it, the lone pair on the pyrrole is part of the aromatic system. Okay, because those electrons are part of the aromatic system, they are not active. If we look at the pyridine, pyridine is still aromatic, but it is aromatic through the pi bonds on themselves. That nitrogen being sp2 hybridized, the lone pair cannot count towards the system, and that lone pair is not involved in resonance. Right? So it's not aromatic. It is really bothering me that I actually goofed all of the color coding here, but whatever. Okay, it's not aromatic. Because it is not aromatic, that nitrogen in pyridine could now act as a base. The nitrogen in pyrrole can't. Okay? How could we see that or verify and be like, is that actually true? Well, we could actually look it up. Okay? We could have it act as a base and see what happens. Okay? In that case, they would both accept a hydrogen, and really what we'd be looking at or wanting to know is what are the pKa's of these individual species. The lower that pKa, the more acidic that structure is, and if it's more acidic, it is less likely to form than the other one. Okay? And you might already know that we see that in the arrows that were used or chosen for this, which was a bit misleading, but not misleading, but foreshadowing. The pKa for pyridine is about a 5.2. That's still pretty acidic, but it can still act as a base. The pKa for our pyrrole, 0.4. Okay, significantly more acidic. Okay, that aromaticity is lost when you acidify, when you put a hydrogen on it. You no longer have that lone pair, and that structure is now anti-aromatic. Really doesn't want to be, and it's actually not anti-aromatic, it's non-aromatic. It doesn't want to be non-aromatic. It really wants to get back to that aromatic lower energy state. And so it tries to shuttle that hydrogen off as fast as possible, thereby reversing the reaction. Okay, what does that mean? Pyrrole, not very basic. Pyridine, okay as far as basicity goes. Okay? So aromaticity can allow us to predict these kind of things. For those of you saying, God, it's another thing on that charge size, not really. Aromaticity is all about resonance. Why is the pyrrole less basic than the pyridine? The lone pair is involved in resonance. Resonance can explain the difference in acidity. Aromaticity just happens to be the uber specific case of resonance. Okay, so it's not really a new thing. We're just applying that content. Okay. A little bit of foreshadowing. If we took a look at this molecule, what kind of chemistry might we expect? Okay, well, we might look at this and say, well, that carbocation is unstable, and because of the hybridization of this carbon, that is sp3 hybridized, I don't have an aromatic structure. So if I were to say lose one of these bonds, I could take those electrons and I could put them into that structure. That would thereby fix the positive charge and it would achieve aromaticity. Okay? And it turns out that's exactly what happens. This hydrogen ends up being very, very acidic and falls off the structure fairly quickly. Okay? And the result is that we end up with an aromatic structure. Okay? So we can predict something using this kind of chemistry. Okay? What could we predict? Ta-da! There's our big summary of reactions. And I believe that's what our next video is actually going to boil into. It's going to look at that far left, way over there. And it's going to look at each of those things in red. We'll explore a little bit of the things in purple, in blue. but those big categories in red are our primary reactions. After we understand how we put a new piece on, then we'll actually look a lot more in depth at the overall reaction itself and how it actually happens, and for that point, to get X, how that X affects the overall reaction and the substitution. Okay, how? That's this section down here, are activators and deactivators. Okay, so really all we're trying to do is categorize these things, and once they're categorized, it just works. It's amazing. Okay, with that, I think we're done. Yep. Thanks for listening.